Hi, in this video we are going to talk about a version of Shannon Sampling Theorem, which is an important result in signal processing applications or in signal analysis in general. Now our starting point is a signal x of t, but x of t is not arbitrary. X of t is a band-limited signal. By band-limited, we mean that the Fourier transform of x of t, or x of omega, vanishes outside a certain band of frequencies. So x of omega is the Fourier transform of x of t, and the word band limited implies that x of omega is equal to 0 for magnitude omega greater than omega m. In other words, for omega greater than omega m and omega less than minus omega m. So if we show this in terms of a symbolic plot of magnitude of x of omega, because x of omega is in general complex valued, so here we just draw the magnitude of x of omega, so it will be only non-zero in the interval from minus omega m to omega m, and it will be 0 outside this interval. Okay. Now, suppose that we multiply x of t by an impulse train, a periodic impulse train. So let p of t be the periodic impulse train, and from minus infinity to plus infinity, delta of t minus m ts. So we have impulses at 0, ts, plus minus 2 ts, etc. Let us define the signal xs of t as the product of x of t with p of t. In other words, x s of t is equal to m from minus infinity to plus infinity x of m ts delta of t minus m ts. So we have this operation, and this operation is called sampling x of t by the impulse train. Now, here there may be a question related to the following. we know that the impulse signal is only a signal model. Therefore, this operation we carry out, that means sampling by an impulse train, is also a process in terms of our signal models. Okay? But we are going to see that this modeling approach is quite useful in obtaining certain important results. Okay, so here as an explanation, we write the following. X of t is sampled by the impulse train. Okay. Now this is the operation we carry out in time domain. So every operation in time domain has a counterpart in frequency domain. So what is the frequency domain counterpart? Now, we apply Fourier transform on the signal x of t, which is equal to x of t times p of t. Okay. Now, we know that the Fourier transform of a product of two signals will be 1 over 2 pi times the convolution of the Fourier transforms. So this is the modulation property of the Fourier transform by the modulation property of Fourier transform we have xs of omega equal to 1 over 2 pi x of omega convolved with p of omega. Now what is p of omega? P of omega is the Fourier transform of the impulse train. But remember, in order to obtain the Fourier transform of periodic signals, first we obtain the Fourier series representation of the signal, and then we obtain the Fourier transform. So Fourier series representation of P of t is P of t. Now P of t is periodic with fundamental period Ts, and we know that P of t will be in the following form: k from minus infinity to plus infinity, ak e to j k omega st, where omega s is equal to 2 pi over ts. And ak is equal to 1 over ts. Remember, we integrate over a period, so we integrate from minus ts over 2 to to Ts over 2, and there the signal is delta of t. So we have e to minus jk omega st integrated with respect to t. So the coefficient ak is Ts. So P of t is the Fourier series representation. In fact, we have obtained this result in some of the videos before. 1 over Ts e to j k omega st. So once more, we repeat an important observation related to this Fourier series. All Fourier coefficients are equal, even for arbitrarily high frequencies, for k in magnitude. If we can choose k arbitrarily large in terms of magnitude, and those correspond to very high frequency components. So even very high frequency components are represented equally in the Fourier series representation, which in fact is related to the singular behavior of the impulses in the impulse train signal. Okay, so this is the Fourier series representation of P of t, and the Fourier transform is, okay, let us show it by P of omega. It is equal to k from minus infinity to plus infinity, 1 over Ts, 2 pi delta of omega minus k omega s. Okay. Therefore, xs of omega is equal to 2 pi's will cancel out. So we have x of omega convolved with k from minus infinity to plus infinity, 1 over Ts delta of omega minus k omega s. Okay, now convolution with an impulse is very straightforward. So xs of omega, the Fourier transform of the sampled signal, is equal to k from minus infinity to plus infinity. Okay, let me write it here. X s of omega is therefore k from minus infinity to plus infinity, 1 over Ts, capital X of omega minus k omega s. Okay, so this is the Fourier transform. Now the result we obtained in frequency domain will give us a lot of information about the nature of this sampling operation. So now we have to try to interpret this result in frequency domain, and we are going to try to answer the following question. Is it possible to retrieve or reconstruct x of t from its samples? The answer to this question will be known as the Shannon Sampling Theorem. Okay, so let us look at this problem in more detail. Okay, we have obtained the Fourier transform of xs of t as xs of omega, and the expression is k from minus infinity to plus infinity 1 over ts capital X of omega minus k omega s. In other words, we have obtained xs of omega in terms of a linear combination of shifted versions of x of omega in frequency domain. Okay? Now, we remember that x of t is band limited, so this is quite important at this step. Okay, by band limited we mean that the Fourier transform of x of t vanishes outside the band of frequencies. So if we plot magnitude of x of omega, it will have such a plot. It will be non-zero from minus omega m up to omega m. In other words, omega m is the highest frequency component present in the spectrum of x of t. Okay. Now, remember, omega s is equal to 2 pi over ts. Now we are going to give a name to ts and omega s. Now ts is called the sampling period. And omega s, which is equal to 2 pi over ts, is called the sampling frequency. Now, let us consider an approximate graphical representation of xs of omega. As we have already mentioned, xs of omega is composed of shifted versions of x of omega in frequency domain. So if our sampling frequency omega s is less than 2 omega m, the approximate graphical representation of s of omega will be in the following form. Okay. Again, since excess of omega is in general complex valued, we are considering only the magnitude graph. So since omega s is less than 2 omega m, the shifted replicas of x of omega will overlap in this case. Okay? So this is the zero frequency. This frequency is omega s. This is 2 omega s, etc. This is minus omega s, and so on. So we have in this case shifted replicas of x of omega overlap. Now this phenomenon is called in signal terminology aliasing. So we have the aliasing phenomenon. The shifted replicas will overlap. Now on the other hand, if omega s is chosen to be greater than or equal to 2 omega m, again, let us denote an approximate graphical representation of excess of omega. So this is omega, and this is, again, we are only plotting the magnitude. Okay, in this case, we will have no overlapping. Okay, this is 0, this is omega s, 2 omega s, etc., minus omega s. So we have no overlapping in this case. So in this case, something very interesting will happen. We will be able to retrieve x of t from xs of t without any information loss. How can we do that? The answer is very simple. As we see from this graph of the magnitude of excess of omega, we have shifted replicas of x of omega, so we can retrieve x of t or x of omega equivalently by using a low-pass filtering operation. So if we choose an ideal low-pass filter with cutoff frequency, for example, equal to omega s over 2, we will be able to retrieve x of t exactly without any information loss. So in this case, x of t can be retrieved, or we can use the term reconstructed, okay? Reconstructed from excess of t or from its samples by using an ideal low-pass filter with the following frequency response. Remember, frequency response is the Fourier transform of its impulse response. H LPF, representing low pass filter of omega, is equal to, okay, remember in the representation of excess of omega, for each shifted replica of x of omega, 1 over Ts appears as a multiplier. To get rid of that multiplier, the magnitude of the low pass filter will be chosen as Ts for omega less than omega s over 2. And 0 otherwise. So if xs of t is fed as the input signal to this ideal low-pass filter, xs of t is the input signal of this ideal low-pass filter, the output is x of t. So the for the input signal xs of t, the output signal of this low-pass filter is x of t. This is in fact the statement of the Shannon Sampling Theorem. Now, the Shannon Sampling Theorem has many different versions and different interpretations. Here, in terms of our analysis, the result, which is known as the Shannon Sampling Theorem, can be stated as follows. If x of t is a band-limited signal, okay, with the highest frequency component equal to or chosen as omega m, so its Fourier transform vanishes outside the band from minus omega m to omega m. So for such a band-limited signal, if we sample the signal with a sampling period Ts and a corresponding sampling frequency defined as omega s, which is equal to 2 pi over Ts, if omega s is chosen to be greater than 2 omega m, greater than or equal to 2 omega m, it is possible to retrieve x of t from its samples or from xs of t exactly without any information loss by means of an ideal low-pass filter with cutoff frequency chosen as omega s over 2. Okay, thanks for watching.